Okay, so welcome back. We've got our last recitation hour for Module 4 here, so we're just going to walk through some problems that were requested in the class discussion. So for number 65 in 10.1 was the first one. So this problem said if we have some function s of x, and it is given by 5 plus 1 over x plus 5 plus x. And we have some k of x that is just x plus 5. And we know that s of x is really some function v of k of x. Then what must be v? Okay, so playing with the ideas of chaining functions together, if I have the output and the very input, what must have been the intermediate step, right, this v, if it took this as an input and got me this as an output? Okay, so here's how I think about this problem. I think there's about probably 7 different ways that you can do this. I see this x plus 5 as the input, right? So I see this as the object or the input. So what I'm going to do is look for this in the statement of the output, right? So over here, where do I see x plus 5? Well, I see it here, and I also see it, right, like kind of out here. This 5 plus x is another kind of instance of this object x plus 5, the input. So this 5 plus x is in 2 spots. So if I rewrite this as instead x plus 5 plus 1 over x plus 5, we see that I've got that input here and here, right? And so really what this would be taking s of x is really v of, well, what's k of x? K of x we said is x plus 5. It took that input and mapped it to here. So then it must be the case that v of x is the function that puts something right there and right there, right, to kind of speak informally. So whatever that input is x is the placeholder. So v of x is x plus 1 over x. So that's the way I would do it. I think that, I saw this straight away because this was pretty clear, but I could see this being one where you'd need to do some back and forth, some iteration. If this were even like a 6, if we changed the problem, I could see breaking this apart into 1 plus 5, and then, oh, hey, here's the x plus 5, and going about it that way. So I'm sure it looked easy when I did it like that, but really this takes some guess and check, right? Kind of play with it and massage it out. And then for 10.2, number 37. Okay, so for this one, we're asked to find the inverse function and assume that these functions are on domains where they're invertible. So we don't have to worry about any domain issues here. We just need to find the formula. So, if this is the output y is some function O of x, then what we're really looking for is x as an inverse function of y, right? So what we can do is set ourselves up with this equation and solve for x in terms of y. So how would I start doing that? Well, one thing you could do is multiply both sides by the reciprocal of this. So multiply both sides by 1 plus 1 over x over 1. What that does, since this is really just a number over itself, over here it will reduce, and we'll be left with 1 equals y times 1 plus 1 over x. And you might be tempted to distribute the y in, but that actually makes this thing more intermixed when we're trying to separate the variables. So what I'll actually do is multiply both sides here by 1 over y. You see what that does? It gets rid of y on this side. I'm left with just 1 over y times 1 on this side equals 1 plus 1 over x. And then again, to isolate the x, I'm going to subtract 1 from both sides. So I'll get 1 over y minus 1 equals 1 over x. And so in order to find out what x is, we have the reciprocal of x. We're just going to flip both sides, essentially, right? So you can just say, one way to do it would be to just take 1 over, right? 1 over. We'll be left with x on this side, and then 1 over y minus 1 on this side. You could leave it like this. Typically, we don't like having complex fractions. So what you can do is simplify that down here by getting a common denominator. So saying this is really 1 minus y over y in the bottom equals x. And then we can just divide by this, and what you'll get is y over 1 minus y, since that's just the reciprocal. So this is probably a better answer, but really these are equivalent. Okay, so there's a few ways you could have done that as well. You could have started with that up here, right, and rationalized, or not rationalized, yeah, gotten that denominator to a nicer spot, brought it up top, and then solved for x. But you should really end up in the same place. Okay, so next up is 10.2, number 41, and then 49. Okay, so here we have another function. We're looking to find the inverse, and then also interpret what it means since we're given a context here. This isn't just a function in space. So first, to find t as an inverse function of p. You notice I added the t here because I knew that was my input variable before, so now it's going to be my output. Okay, so given p is 10 e to the 0.02t, what I want to do is solve for t in terms of p. So I'm going to start to isolate t. So I'll divide both sides by 10, or multiply by 1/10 on both sides. To cancel that, we'll get p over 10 over here equals e to the 0.02t. Got to remember how to solve for the exponent in an exponential expression. We use logs, so I'll use natural log on both sides because this is base e exponent. And so on the left, I'll get ln of p over 10. On the right, I'll get 0.02t times the natural log of e. And we all know that that is equal to 1. So that simplifies down. And then this is now just a linear equation solving for t. So I'll divide both sides by 0.02. And so we'll get t is equal to ln of p over 10 all over 0.02. I'm not really happy with decimals and fractions. So, 2/100ths is really what that is down there. So 10 over 2/100ths, which is really like multiplying this whole thing by 50. Okay, so this is the formula for t in terms of p now. Okay. So what did we do to find the inverse function? We switched input and output, right? F normally takes input and maps it to output. In our case, our input was time, and our output was what, the account balance? No, this is population, sorry. Population. In millions. So what F inverse is doing is it goes from the population as the input and gives us an output of time, right? So what does that mean an interpretation. Well, what it means is, and are we given a specific value here? No, just interpret the function. So f inverse of p is the function that tells you how long it will take in years to reach a given population in millions. Right, so t equals f inverse of p. If you tell me, or ask me, how long is it going to take for 300 million people to be in this particular area, we could come up with the number of years that it would be. Okay, so, or that it would take. So that would be my interpretation of what f inverse of p means, because we've swapped input and output, so now the output is the independent variable and the input is the output, and this is how we would do that algebraically. So now we'll move on to number 49. Okay, number 69, not 49 here. So we have the harmonic mean of x and the constant a is given by f of x is 0.5 times x to the minus 1 plus a to the minus 1 all to the minus 1. Find the inverse function f inverse of x. Again, this is typically how we write it conventionally, but we're given it in this form, y equals f of x, and so what we're looking for here is x is an inverse function of y. Let's make y the input and x the output, but then we'll map it back over to this notation. So if I have y is equal to 0.5 x to the minus 1 plus a to the minus 1 to the minus 1. Isolating for x, so we'll start with this scalar multiple here. Divide both sides by a half. Right. Divide by half. And it's like multiplied by 2. So we get 2y on the left, and x to the minus 1 plus a to the minus 1 all to the minus 1 on the right. So we've got our variable locked up in here. It's being raised to this power of minus 1. So what you can actually do is raise both sides to the minus 1 power, because what will that do? Well, these powers will quote-unquote multiply, right? And you'll get back to the first power. What you're really doing by raising it to the minus 1 power is taking the reciprocal, right? If we have 1 over a equals 1 over b, all we're doing is say, hey, let's quit messing around and just say a equals b, right? So that's really what's happening here. We're using algebra to do that, so we'll be left with just x to the minus 1 plus a to the minus 1 over here equals 1 over 2y. Notice the 2y, both factors there are getting set down to the bottom. And so now I'm solving for x, so I can subtract this a to the minus 1 from both sides, which is really, just 1 over a. So however you want to think about that, but I'll say, okay, this is 1 over 2y minus a to the minus 1 equals x to the minus 1. So just undoing that subtraction. And so let's write this out actually without the negative exponents, because that might help. All right, so we have that. And so what we want to do is flip both sides, right? If I raise this side to the minus 1, raise this side to the minus 1, we'll get x equals something in terms of y. And so we'll get 1 over 2y minus 1 over a. You say, well, isn't that the same as just flipping both of those? Not really, because we have subtraction here, right? So division would break the order of operations. So what we can do is now just get this to a better spot by getting common denominators down here. So multiply this side by a over a, and this side by 2y over 2y. So I'll get a minus 2y over 2ay in the bottom. So that, let me be super clear here. So this here came from this here. I know fractions can kind of throw us for a bit. So then 1 over that is really just the reciprocal. So we get 2ay all over a minus 2y, and this equals x. Okay. I have not confirmed what the back of the book looks like. It might be like this, or it might be slightly different. You can always check yourself by either graphing or going to Wolfram Alpha to see if two expressions are equivalent or not. But this is how I would go about this one here. Okay, again, anytime you saw me like apply an exponent rule or something like this, would be a place where you could make a different decision based on notation, or sometimes, if two things are being multiplied, you can use a commutative property to do it in a different order. So it might end up looking different, but really they should be equivalent. So those are all the questions I received. I hope you found those helpful, and best of luck on the assessment.